Okay, so what we will do is in this Zoom session, we would be discussing about the discrete Fourier. We start our discussion about the discrete Fourier series. In particular, the last two videos that have been posted on YouTube. First one is an introductory lecture to the DFS, and the second lecture is we are solving some examples for DFS. Followed by we are also looking at the relationship between the DFS and DFS is basically computed for a periodic discrete time signal. And suppose if you take just one period of that signal and compute the DTFT of it, how is it related to the DFS? So these are the topics that we would be again revising and trying to answer your questions or doubts in that. Okay, that's the agenda for today's Zoom meeting. Let me now move on to the screen share mode. Let me go to this OneNote, my notes. Okay, so this is what we will start first our discussion with our introduction to DFS, and then we will follow it up with examples and the other topics I said. Okay, so let me now just turn off my video. Wait a minute. Okay. Hope everybody is able to see the desktop of mine with that OneNote notes there. Okay, so what did we see so far? What kind? We have seen quite some transforms by this time, starting from your signals and systems course. If you recollect, you started your signals and systems course for continuous time signals, and you started with periodic signals. Then you moved on to aperiodic signals. Then we started this DSP course. There we in fact started with aperiodic signals in the beginning. So all that the category is still remaining is periodic signals. That's what we would start our discussion in DFS. So just to have a summary of what all transforms we have discussed so far. If you have a continuous time signal, and in that, if the signal is periodic, you had studied about Fourier series, right? Continuous time Fourier series. Then you moved on to aperiodic signals. In that, you started with continuous time Fourier transform, generalization of that Laplace transform. And then discrete time, we right away started with aperiodic signals. We covered the discrete time Fourier transform, followed by Z transform. So what we would be now going through is discrete time Fourier series, which is originally used for representation of discrete time periodic sequences. Okay, and there is a reason why we postponed it till DTFT. It's because whatever the transform that you guys would mostly use, okay, is FFT, or you will be calling that command, which is nothing but a very like a efficient implementation of within that DFT, discrete Fourier transform. I know you have covered it already, you have gone through it a bit in your lab, but for that the basis will be DFS. So that's the reason why instead of starting our discussion right away with DFS, we postponed it till we cover DTFT, because DFS, from that a natural continuation of that to even finite aperiodic sequences, the transform DFT will stem from DFS. Okay, that's the reason. Fine. With that, let me then, as I mentioned, what we are going to study is a discrete time signals that are periodic. Okay, you all know what it means by periodicity. So if you have a sequence, we are talking about discrete sequences, so I'm using the square brackets. Again, we would be moving on, we would be making switch. Okay, switches, we will be switching between a periodic sequence versus a sequence that is made up of one period of that periodic sequence. So that's the reason why we'll be using this tilde notation to represent periodic signals. Okay, so what do we mean by a periodic sequence with a periodicity of n? The same value would repeat at suppose there is at n equal to 1, your periodicity is 10, the same value would be repeating at 11, 21, 31, and of course -9 and so on. Okay, that's why. So this is how we could say the signal is periodic with a periodicity of n, where x of n plus rn. R is an integer that can take both positive and negative values. Now earlier, like any other earlier transforms, here also we need to come up with the synthesis equation and analysis equation. Okay, what the initial treatment we do is an empirical or an intuitive one. To do that, let's recollect what you guys have done for a continuous time Fourier series, right? You have a periodic sequence. One thing for sure you know is when you have a periodic sequence and trying to represent it in terms of its in the frequency domain, what you would be using, it will be made up of combination of the fundamental frequency and its harmonics. It's not unlike your any periodic sequence. It cannot take all the frequencies. Okay, it doesn't require, in fact, not that it cannot take, it doesn't require. So for that purpose, you could see here, these were the equations I am taking from continuous time Fourier series from your signals and systems course, right? By the way, you have the fundamental, when your k equal to 1, for example, you have your fundamental complex exponential is used for representing these frequencies. Okay, and your omega, this you could, am I writing here? Yeah, continuous time. Omega would be representing your continuous time, which I could write it as 2 pi by t, and all mult k times omega, where k take any integer value in the range of minus infinity to plus infinity, and then a weight given to that. So essentially, the given signal, periodic signal, whose periodicity is capital T, is represented in terms of its fundamental frequency, which is 1 by f, 1 by t if you are talking in terms of hertz, 2 pi by t if you are talking in terms of radians per second. Okay, and it's all harmonics of it. Okay, the harmonics represented by k. Okay, that's what you are very much well aware of it. And then you start, either you take, either write this equation and then from that derive then what would be the value of a subscript k. Okay, this being periodic, or one period you had to do minus t by 2 to plus t by 2, and here if you have a complex exponential of e power j 2 pi by t, you get the same thing with the negative sign here. And then ak is in the frequency domain, so you have the integration with respect to t, or one period you would be doing it, right? Then you also know the derivation of it from your previous course. Okay, now we are moving slowly from the continuous time domain to the frequency time domain, the discrete time domain, sorry. So what would happen now? Your t, which is a continuous variable over time, is can take only discrete values that turned out to be capital N. Your capital T periodicity, now you represent it as if it is capital N. Okay, and then x tilde of t will become that, and in place of what do you expect here? Okay, all this I'm doing to just give you some intuition on why we arrive at those equations. Anyway, in the next video lecture, the second video lecture that I have posted on DFS as a problem for deriving these expressions. Okay, yeah, coming back here, this e power j 2 pi by t kt, if you have it, then what's happening here? This t is getting replaced by n, your small t is getting replaced by small n. Anyway, k is an integer which is harmonics of it, so that would remain the same thing. Okay, so unlike t here, the moment you switched it to n, if you recollect the earlier classes of our DSP, this has that is what, once the variable is changing from small t to small n, that's bringing the periodicity into the picture, right? We have done that, and then we were proving also why DTFT is periodic with a periodicity of 2 pi and all we discussed during that. The same logic holds here. See, mathematically k and n behave same. So there is not only periodicity in terms of k, but also in terms of n. These two periodicities are there with a periodicity of n. Okay. So what does, yeah, those derivations and this discussion, we had a very detailed discussion in that video if you have followed it, right? So from that, what you could see here, there are two conclusions that we could draw here, is that this complex exponentials, okay, there are each harmonic. So each harmonic is for each value of k, okay, k representing the harmonics. Each harmonic is periodic with a periodicity of capital N. Simply you take here in place of n, n plus n, that will again come to the expression with n, because that n plus Rn, that n and the denominator capital N getting cancelled out. So each, then essentially the harmonic for a given value of k, the same sequence would repeat, is it not? So that's why each harmonic is periodic with a periodicity of n is the first conclusion. Now the same thing, n and k after all mathematically are just different variables. You could exchange the names of those variables. So from that you would get that there are only n distinct harmonics, and after that they also would repeat. So where are we arriving with that? Is that if you have a discrete time periodic signal, when you are trying to represent it as a combination of the fundamental frequency and the harmonics, okay, then there are only n harmonic, including the fundamental frequency, if you call it, there are only n harmonics that are required, first thing. And the second thing is, each harmonic has a periodicity of n again, okay. That would help us to bring the equation. So relook at these equation here. You cannot have k from minus infinity to plus infinity because there are only n distinct values. So you change this to 0 to n minus 1, the first change there. And these are, now you have discrete. Well, see, earlier you have this x tilde of t is a continuous variable, so you had an integration. But now that in that place you got x tilde of n, so that's a discrete. Here you have summation for ak, the first change there, okay. And yeah, so this is going to be discrete. And then this is not from minus t by 2 to t by 2. Again, it is each harmonic. This is essentially the weight given to each harmonic, okay. That is what you get there, that you get as a summation now from 0 to n minus 1, because that's all you have the periodicity there. So then yeah, even while defining it, see, you either define let x tilde of t is this and you go here, okay, or that's how you do it. But you could have moved it to here as well. If you wanted, you could have moved it here, then this would disappear here. So that's how we define the discrete time Fourier series, okay. Why we do it, that should have been already clear to you from the second video lecture, where we have related the DTFT of one period of this discrete time signal to the DFS of that periodic signal. So that with thanks to this definition, when we moved 1 by n to the x tilde of n, we are able to get it very nicely, where the x tilde of k, that is the DFS coefficients, are simply the samples of DTFT of one period of that signal. So for that convenience, this has been moved there, okay. There is no hard and fast rule that how x tilde of t should be there. We follow certain conventions. So this is the convention that we follow. We could have defined it the other way around. There is no problem mathematically with that, but this is what we go with, okay. 1 by n into k varying from 0 to n minus 1, x tilde of k e power j times 2 pi by n into kn. Now x tilde of k would be now in place of j, you have minus j there. That's all. Those are the synthesis equation and analysis equation, okay. Then we were also having a look at the frequency domain properties of these different transforms that we were doing. So essentially the transforms, again we are coming back to the same classification of signals being continuous and discrete, and then each of those signals being periodic and aperiodic. This is a very interesting relationship that you should keep in mind. Suppose if you have a periodic signal, right, then once it's a periodic, you know that while you are representing in the frequency domain, all you would have as the frequencies is the fundamental frequency and its harmonics. So you have only a discrete signal in the frequency domain, right? Because it can be, you could have weights for only the fundamental frequency and its harmonics. So that's why the moment you have a periodic signal here, you have a discrete and both are discrete. So the other way around is also true. The moment you have a discrete time signal, okay. So if you recollect what we did from sampling, a discrete time signal in the time domain can be represented as a given continuous time function multiplied with impulse time, which is equivalent to convolving with impulse train in the frequency domain, which means you are placing multiple copies of the same thing, which means it is periodic, is it not? So the moment it is discrete, so see here, when it is discrete, it is periodic in both the cases, right? And when the signal is periodic, okay, so by the way, the first column and the first row are the signals nature in the time domain, okay, the other in between, the that one written in blue is giving you the properties of it in the frequency domain. Okay, the moment your signal is periodic, it has to be discrete. So the nice thing here is what we are discussing now is a periodic sequence in the discrete time domain. So now the interesting thing is the signal is discrete and periodic in the time domain, as well as discrete and periodic in the frequency domain. And another interesting thing is, if you have a periodic signal, a periodic sequence in the time domain is having n components, the consequence of all these things is that you just need n frequency coefficients to represent that signal. So for the first time, you have a number of coefficients equivalent to, in the frequency domain, that are required, same as the number of the actual signal that is there. So a periodic signal, it's enough to represent n coefficients, right? After that, in the time domain, it just repeats. So the same thing in the frequency domain as well. So that's the introduction to discrete Fourier series. Okay, so before we move on further, are there any questions here? Do you have any questions so far for the discrete Fourier series before we take a look at some examples there? Are you able to follow this? Is it like your mobiles or laptops from which you are logging in doesn't have a mic? For most of you guys, it looks like, except Yashas, whom I am forcing to talk sometime. Maybe I should take an attendance kind of thing so that at least I could listen to you at least once in the whole Zoom session. Hope you are all awake. Not only you logged in, but you're not sleeping, I hope. Okay.
Yeah, clear, sir.
Yeah, it's clear, huh? Right, good. So this part, I think you already discussed a bit in your DSP lab also, is it not?
Yes, sir. Pujaman explained.
Good, good. So can I go ahead with the second part of this DFS? Then if none of you have any questions. Okay, I assume there are no more questions since no one is raising anything, right? I'll move on to the second part. Okay, let me again share the screen. And go back to this DFS part 2. Okay. Yeah, so now we are going to see some examples followed by the relationship between DTFT of one period of the signal versus the DFS here. Okay, give me a minute again. Let me turn off the okay. Right. So I'm just rewriting the equations here, and then we started with an example of an impulse train. The impulse train having a length of n. Okay, that means for every n values there is one sample here. Okay, so for example, if I write it as delta of n minus rn, r varying from minus infinity to plus infinity, what does that mean? If I have a value at 0, so that means 0 minus Rn. Okay, R equal to 0 means it would be at 0 only. N means next time when n equal to capital N, the same thing would repeat. So then you have a value at capital N, 2n, and so on, right? And of course, this is minus n, assume that, then you have it minus n, minus 2n, and so on. Okay, this is the one, your input sequence x tilde of n. You would like to compute the DFS of it. So what's the definition of DFS? 0 to n minus 1, x tilde of n into e power minus j 2 pi by n into kn. So you are going to vary your n value from 0 to n minus 1. It does have a value at 0, but next value is there only at capital N. So there is only at n equal to 0, this value is going to be 1. Otherwise, this is going to be 0. So you just simply, there is no summation. In fact, there is only one term here, that too when n equal to 0. So n equal to 0, this is 1. N equal to 0, e power minus j0 is 1. So what you are getting is here 1. So what does that mean? If you have an impulse train, so this you could plot it from 0 to n minus 1, or this is everywhere 1, in fact. Okay, so that's what you had as a signal here, your Fourier in the Fourier domain. Okay, we are now, this we know, this relationship, this we worked out, but to get in other interesting relationship, what we are doing is now we are starting with, for example, given that the DFS is 1 with a periodicity of capital N, what would be the corresponding x tilde of n? That's what we are trying to compute here. Okay, then what would be that? X tilde of n equal to 1 by n, k varying from 0 to n minus 1, x tilde of k into e power j 2 pi by n into kn. And for 0 to n minus 1, this is all, everywhere this is 1, correct? So all you have is 1 by n, k varying from 0 to n minus 1, e power j. This is all you have it. So you already know that x tilde of n equal to, this value is 1 at n equal to 0, and it's plus r times n, okay, at all those, and then it is periodic. For all other values from 1 to n minus 1, this is 0. So that means what you could say here is, if this n value is not equal to 0, okay, this, make a note here, this has nothing to do with this summation. This is what we are talking about, is this n value. Then what is the summation is going to happen? Let's see the trivial case, what is happening when your n equal to 0. Okay, this inside of the whole thing is 1 irrespective of which k value, because anything multiplied with 0, you essentially have that in the complex exponential power. So this is 1, k summation from 0 to n minus 1. So you are adding 1 n times, so that would give you n. N or n multiplied with 1 over n would give you 1. So at n equal to 0, that means that x tilde of 0 is 1, rightly so, right? And then you know, for all other values of n, okay, again keep in mind this is a periodic function. So when I say that for n values from 0 to n minus 1, of course excluding 0, because that we already treated it. Okay, so then this is going to be 1 by n summation of k varying from 0 to n minus 1, e power j 2 pi by n into kn. Okay, so in other words, you have in the denominator n 2 pi n, and this value you are varying from 0 to n minus 1, and summing up all those exponentials, okay, that would give you a value of 0. Okay, that's yeah, if you just, if I give you only just this part, it may not be so obvious to look at it, but you can substitute some values, and then this is anyway is already a proof of it, because we did the other way around and then we are seeing it in the reverse order. So the proof is done. To get some intuition, to take for example n equal to capital N equal to 2 here, okay, you substitute that, and n equal to 1 if you take it, that would be, yeah, you should be comfortable with drawing some e power j times 2 pi into some value, okay, some x, something like that. So that you should be convenient to draw. So for example, this is your real axis, this is your imaginary axis. So e power j0 means it is here, and then j pi by 2 would give you here. Anyway, e power j omega, okay, that value magnitude is always equal to 1, right? Because square root that cos omega plus j sin omega. So magnitude wise, this is going to be 1. Okay. But all the phasors needs to be added there. That's what would happen. So then you could see here, if you take capital N equal to 2, you will end up with these two phasors. Okay. Since they are on the unit circle at the end, the magnitudes wise, they would be same. Phase wise, they are opposite. So that becomes 0. Okay. So for example, you have capital N something like 3, then you would end up with phasors which are 120 degrees apart. Okay. So when they are symmetric, 120 degrees apart, having all the same magnitude, that's in fact you would get when you are going to deal with 3-phase circuits. Okay. If I'm not, if you have already did that, you would be doing that summation. That would be also equal to 0. And every time the n value is even, this is very so obvious. For example, n equal to 4, you would be getting something like this, all these functions. Okay. And the other thing, so they will be cancelling the opposite ones. The phase themselves will be cancelling out. That's just to get some intuition about it. Okay. This is the result you should keep in mind, particularly for proving your the DFS equations. That you will come across that again there. So 1 over n, k varying from 0 to n minus 1, e power j 2 pi by n into kn would be equal to 1 when n equal to 0. Because n equal to 0, you are summing up 1 n times, that would give you n. N divided by n would give you 1 and 0 otherwise. Okay, this is something you should keep in mind. And then I asked you to, I think that exercise is a little later. Okay, the second problem we tried to do is, example we tried to do is having, earlier we worked out for 1. Okay, you started with the impulse, we started with this impulse time, you arrived at 1 here. Okay, then suppose you have with some variations an impulse time here. Okay, that what would, so that's what we are in fact here analyzing the property of duality. That's what we are doing here, if you notice here. So multiplied with the n and then impulse time, this is your DFS. Okay, then what we are looking at is what would be the corresponding then the DFT of it. So that would be equal to 1. Okay, so this is the duality property. I'm sure you all are clear with this duality property because you have done it in different instances. It's not very difficult. You could see here the differences between these two expressions. Okay, you have 1 by n here, there is nothing here, that multiplication is difference, and then there is a negative sign here, there is a positive sign here. So if you could somehow switch them, that would give you the duality property. Like for example, you start from here, you multiply on both sides with n, that would give you n times x tilde of n would be equal to summation over k varying from 0 to n minus 1 x tilde of k e power j times 2 pi by n into kn. Okay, I would like to arrive at the second expression from the first expression. So what should I do? The next change, what should I do here to get the second expression? So the summation I want to get similar to the second summation. So similar to from synthesis, I want to start and arrive at the analysis equation. So what's the next change I should do here? What's the next step? Anyone there? I would like to start from the first equation and get something similar to the second equation. So what should I do for that? One thing I did is I got rid of that. There are only two changes, right? A multiplication and a sign change. I already accounted for the multiplication factor now. The summation on the right hand side, I want to get similar to the second expression. So what should I do now? What should be the next step?
So we will take x tilde of minus n.
That's all. So suppose if I replace n with the small n, so that would give me x tilde of minus n. Substitute that, would give me k equal to 0 to n minus 1, x tilde of k, wherever there is n you keep a negative sign, so e power minus j 2 pi by n times k times n. Okay. What's next? Well, these are just after all a variable k. Can I switch k to n and n to k, the variable names? There should not be any problem with that, is it not? So let me do that also. Suppose I could write equal is replace wherever n is there k and wherever k is there n. Okay. If you want, you take an intermediate variable and do it if that is not so clear to you. Okay, n times x tilde of minus k is equal to n times 0 to n minus 1 x tilde of n into e power minus j 2 pi by n times k n. Okay, so if I give you this equation, okay, what could you say from this equation? For example, you could say the DFS of whatever is here, right, which is x tilde of n is equal to this one, x tilde of k, is it not? Similarly, you now tell me from here, what can you say here? DFS of x, capital X tilde of n, okay, will be equal to n times x tilde of minus k. That's all. This is the duality property. So if you know one DFS, you know the other DFS. Okay, for example, if you know for x tilde of n, small x tilde of n, the DFS is capital X tilde of k. You already know that for capital X tilde of n or k doesn't really matter, but just for consistency, in the time domain we are using n. That's all. That's after all a variable. That would be capital N times x tilde of minus k. So if I have to say it in words, for x tilde of n, you got x tilde of k. Now, for example, if you flip that signal, that would give you x tilde of minus k, right? And yeah, so you got for, yeah, let me write it in this way, x tilde of n, the DFS, you got it as x tilde of k. Now, if I ask you, what is the DFS for x tilde of k? What you should do, you take the signal, you flip it, and that would give you x tilde of, I could have written n with k, it doesn't really matter. That flip it, that would give you minus k, multiply it with the periodicity. Okay, that's the DFS of it. That's all. So here, for example, we did the same thing here. This you flip it, doesn't really matter flipping, because this is varying from minus infinity to plus infinity. You have the same signal. Look at here. Even if I flip that signal, that would remain the same. And then you multiply with n. So that's exactly what has been given in the second expression, right? And rightly so, now you got there as 1. Is that clear? Right. So then I asked you to prove this, given that if x tilde of n equal to this first expression, that's how you define x tilde of n. I asked you to prove that then x tilde of k, the second equation, the DFS equation, is what you arrive. Yeah, again, one word of caution for you while writing these equations and trying to derive these equations is pay attention to the variables that you are using, whether R, K, so you don't get confused, and you should have a very clear interpretation. For example, if I had written here K, and while you are substituting, you might mess it up with the variable which is there on the left hand side, which is different from the summation. So that's the word of caution. You just pay attention to the names you are giving, and make sure two variables are not given the same letter to represent them. Okay, that's all. So if you want to prove it, it's very simple. This x tilde of n, you take the right hand side of this equation, you substitute here, okay, and then you try to simplify this. That's all. Then you would end up with just x tilde. When you substitute here, there is an x tilde of r here, okay. This variable you could take anything, doesn't really matter. So there is capital X tilde function is here, so that simplification would give you this also would come to your rescue. This relationship would be useful for you in that simplification. That's the exercise for you. Hope at least some of you had tried for it already. Okay, Then the second part of this second video is about you have an x tilde of n the signal. Out of that, I took one period of it. I compute the DTFT of it. I already have this being periodic. I have DFS of it. So how are these two related? You would realize that this x tilde of k is nothing but a sample version of x of e power j omega. Very obvious from these, simply writing these two equations. So for example, x of e power j omega is x of n into e power minus j omega n varying from minus infinity to plus infinity here originally. But your signal is you are taking just one period, and beyond that, that signal is 0. So it's enough if you take 0 to n minus 1. And again, in this range, x of n and x tilde of n are same. So I'm replacing x of n with x tilde of n. Okay. This is anyway the expression for this equation. And everything is same except that now in place of omega, you have 2 pi by n times k. Okay. So that means you could say then x tilde of k, which is a discrete time sequence, is nothing but the sample versions of x of e power j omega, samples taken at regular spacings of 2 pi by capital N, okay, times k, and this k varying from 0 to n samples you are taking it, and 2 pi by n into k, that's where you are taking the samples, okay. And then we solve this equation. We solve this problem where half of them are 1 and the rest are 0, okay. And this again, you have quite a few problems like this. Okay, the moment you see 1 minus e power minus j omega phi, you take half of them. Then depending on the signs here, it would be either sine or cosine functions. This is a classical sinc-like function. You would get it, not exactly, but it's something like a rect function. So you would get it like a sinc function. That should get triggered in your mind. Okay, I haven't plotted here again the magnitude and phase, but by this time you should be competent enough to draw it by hand without requiring any tool as such like MATLAB and all any software tools. But anyway, that exercise we have done enough number of times earlier. Okay, so then I had just to add some diversity, one more example where I have a coming back to sines and cosines. Okay, the moment you see it again, see here also, although we have not explicitly talked about it, what you have is essentially complex exponentials are there here also. So if you look at the expansion of it, so essentially you have complex exponentials with some weightage. So the moment you have sine and cosine, you could in fact write them as summation of complex exponentials and compare them with the coefficients here. That should right away give you x tilde of k. That's the idea here. Okay, that's first example that has been given there. Now I am also giving you that I started with a continuous time signal, which is sampling frequency has been given. So from that, you already know this from sampling how to what would you get out of the sampled one, right? That would give you a cos 2 pi by 10 into n. And in the beginning classes of the DSP course, you studied about how to compute the periodicity of it, right? And the moment you have a function like this, you already know that 2 pi by capital N into n, then this would give you the periodicity. So if you are not very clear to it, you just write it again, start from, if you don't remember any of those things, you start from 2 pi by n into small n, okay, should give you here, this should be equivalent to what should be there here to get the equivalent one. Then you will get r times n, and if any of those things is there, that n and this n gets cancelled, so multiples of 2 pi is there, that brings you back to the same point, right? So that would give you the n value. And then all we did is this you have written as complex exponentials, and you want to, this is your x tilde of n, okay. If you write the expression for x tilde of n, you have complex exponentials of positive complex exponentials e power j 2 pi by n k n. So all we are doing is using periodicity and figuring out to what positive complex exponential will this be equal. So that's nothing but, if you write it as j here, n into minus 1, okay, and that you are writing minus 1 plus 10, right? That would give you, it contributes to 9 there. And then you are varying the k values there, correct? So you have k equal to 1 and k equal to 9. yeah, there is that you write x tilde of n, you come back here, there is a 1 by n coefficient here, so I'm writing it as 1 by n, 1 by 10 into 10 times this. So sometimes this is where students commonly make a mistake, either taking, sometimes ignoring about this n, and sometimes instead of writing 10 they would be writing 1 by 10, so that you pay it. That's a very easy thing, but yeah, some be cautious about what exactly you're making, make sure you are doing it correctly. Okay, so that's what you do it here. And with that you have in fact 5a is what you get for k equal to 1 and 9. Okay, and of course if you see later, the moment you come to DFT, I'm saying it, sorry, not here, it's not correct. Okay, later you would be representing it from minus n by 2 to plus n by 2 as we move on. So you could see in fact that would be symmetric about 0. Okay, that's another way of taking the periodicity, but anyway, don't worry about it, we'll come to that a little later. Okay, that's all. And then I have given you an exercise where all that it changes is what is the periodicity of that when you have this. So that's where you need to pay attention and then find out the corresponding coefficients and other things. Okay, and I also then asked you to compute the DTFT of one period of that signal and make sure this relationship is satisfied. Okay, I could have asked a few more things there, because in sampling you have already done, for example, what is the frequency response of xc of j omega. If you are interested, you could try all those things. What would be the xc of j omega? Okay, and then you could also see if you call it as x of n, what you are getting there, the periodic signal. So for the periodic signal, what is the frequency spectrum? And then one period of that, if you are taking, what's the frequency spectrum of that one period versus the DFS of it. Okay, x tilde of k, all those things you could calculate and try to relate them. But yeah, I leave that part to you, but this is the bare minimum thing that you could do here. So with that, we are done with some examples, relationship between one period of your DTFT of one period of your periodic signal to the DFS. Okay, and yeah, examples for that as well. So that's all for the last two classes, last two video lectures. Okay, and yeah, any questions or any doubts so far in the second video lecture or even in the first one? It might take again for DFS, I might require, so 2 classes are over. So this is all the foundation for DFT. We are going towards that. 2 classes are over now. So I might take around, I might make around 5 video lectures. So that means 2 video lectures every time. That means 2 to 3 weeks we will be done with this. And I would require 2 video lectures for FFT. It would be 1 week on FFT. So 4 weeks would be more or less done. 4 or 4.5, whatever. Yeah, 4 to 5 at most will be done with the DSP thing. So we would require 4 to 5 more weeks. Okay. So this week we are done with it, right? So next class is on 4th. Let me see the calendar. 4, 11, 18. Yeah, around, let's see, we might finish. Let's see how it goes. Any questions or any suggestions on whether it is too fast, too slow, too repetitive? Because anyway we are discussing there. So yeah, feel free to give your feedback. No questions on this also? This part also, everything is absolutely clear to you all?
Sir, I have one small doubt, sir.
Yes.
In the second video, like while comparing the relation between x of n in continuous domain to discrete domain, x of e power j omega and x of n.
Right.
I mean, capital X of
Correct.
k or something. Like for the input signal, initially the signal which you considered for this discrete case, it was repetitive, right?
Correct.
It was periodic and it was repetitive.
Correct.
Yeah, in the same page. Like in the second step, this x of n, Why did you consider just only one period, sir? If it's periodic, then it should repeat again and again, right?
Yeah. So that's what we will do in the upcoming classes. So in this class, what all we are analyzing is, if I take one period of a periodic signal, okay, and compute the DTFT of it, how is it related to the DFS of a periodic signal? So that is all we are right now analyzing. Okay, this is also we are doing it keeping something in mind. It's because yeah, it is a bit too early. So pay attention here. This is a very interesting thing that in fact we will be discussing in a very detailed manner in the upcoming classes. But see here, suppose we would be in fact doing the reverse of it in all your DFT. See, you had a signal x of n, a finite signal. You assume that you had a finite signal. Can you not construct from that a periodic signal? Right? If you have this is your x of n, you could always construct a periodic signal with that, is it not?
Yes.
By repeating it. And so if you are constructing that, what you had is x tilde of n there. Okay. And for that, if you have x tilde of k, so for this signal to represent in the Fourier domain, all you require is just, suppose if this finite length is capital N, you just require n coefficients to represent that, is it not?
Yes.
Yeah. Suppose if I give you now these n coefficients of x tilde of k, you could in fact come back to x of n with these things. Suppose let me put it in the reverse way. I give you for a periodic signal x tilde of k, if I give you this, okay, I want to get back x of n. So for example, if I give you x of e power j omega in the first place, I cannot store it everywhere because this is a continuous variable. But if I give you x tilde of k, you simply found inverse DFS of it, okay, that will give you x tilde of n. You have a periodic signal here, and if you know how many point DFT it is, okay, yeah, this is also not required. In fact, from here you could always tell me what is your x of n here. So the whole x of n in the frequency domain, it's too early. I'm trivializing few things, but this is what the background for DFT essentially. So if you take the DFT, that's essentially, it's enough if you keep this just the k. If you have a finite length signal of size n, you would in fact DFT, it is enough you store just the n samples of your DTFT. That's good enough to represent that signal, because if you just take uniformly sampled values, so I'm not sure what I told you is very clear to you, but I assume that I have x of n. Okay, I store x of e power j omega, you get this DTFT. Here you want to do the frequency domain analysis, right? Now suppose if I take n samples of it, okay, uniform samples of it, what do I get here? I get x tilde of k here, is it not? Am I clear? You are there, x of n is there of finite length, okay?
Yes, sir.
Then I am taking DTFT of it. What do I get there? X of e power j omega.
Yes.
Now I take n samples of it. So that's nothing but this relationship. X tilde of k is x of e power j omega at 2 pi by n into k. Will that not give me x tilde of k?
Yeah, it will.
Then you take inverse DFS of it. What will it give me?
The original signal.
No, not original signal. Periodic signal.
Yeah, tilde of n.
Right. From that you just take one period of it.
Okay.
But can you do the same trick with the inverse DTFT? You cannot do that. If you have an inverse DTFT, if you take that with just n samples of it, there is no way you could get back your original signal. On the other hand, you cannot even store x of e power j omega because that's a continuous thing. So the moment you are taking only few samples of it, there is no way you could get back your x of n. But this is where you could get it, is it not? So this is the very basic idea for DFT.
Okay.
So x of n, the x of e power j omega is there. You just take n samples of it, and then you can still get back your x of n. Very interesting stuff. So if you could realize that. So from that you could get, in fact, x tilde of k. You take inverse DFS of it. That's where you get x tilde of n. Take one period of it. That's your x of n. Of course, here you should be knowing what's the length. It should be a finite known finite length. That's all. Then you could get back with just if your signal length is n, you just keep n coefficients of your DTFT and you get back your signal from that, from those n coefficients. That's the nice thing about it.
Okay, sir. I kind of.
No,
okay.
is it clear? Or maybe if you get.
You said you will discuss in detail in the upcoming video.
Yeah,
so.
but try to analyze it for yourself. Try some time brainstorming yourself, contemplating on this, because unless you understand this very clearly, you won't be able to actually appreciate the DFT. The conceptually how nice it is, you won't be able to appreciate it. This forms the basis for it.
Sure, sir. I'll try myself.
Yeah, that's good. So any other hope that makes sense to others as well, whatever I have been discussing? Yeah, you guys also,
Yes,
you also contemplate about it. That's a very important concept. So earlier DTFT, from DTFT to get the signal, you need to kind of compute inverse DTFT. Okay, for that you should have the whole DTFT. You cannot simply take samples of it, and you cannot, there is no way you could get your x of n back. But now we are able to do that. You just simply take n uniformly spaced samples. That would give you x tilde of k. And from that you take inverse DFS. That will give you x tilde of n. From that you take one period of it. That will give you x of n. No other questions? Vaishnavi, I hope you have taken the attendance.
Yes, sir, I have taken.
Okay, good. So if there are no other questions, I will stop the video recording here. Okay. Then yeah, if you have any other concerns also, you could discuss. Let me before that just stop me the recording part. Okay.